Gleb Turner is a consulting systems engineer with A10. He's got 15 years of experience. I think you have more than that. Systems engineers, but yeah. Before joining A10, he was system engineer at technology companies such as BTI Systems, Nokia Siemens, Juniper, Alcatel, a bunch of others. Holds a BS in electrical engineering and mathematics from the University of Tennessee. And with that, he's going to be presenting, let's see here, IPv6 and DDoS protection. Wonderful. Thanks so much.
Thanks, everyone. Hopefully everyone's having a good afternoon and you're not feeling the lunch and getting sleepy and all that good stuff. So I think I have a very good presentation for you today. What we're going to talk about today is security issues, specifically DDoS attacks in the IPv4, IPv6 mixed environments, specifically around your IPv6 migration strategy. And I find this to be a very polarized discussion, to say the least. So I want to talk to customers. They either embrace it or they absolutely hate it and they throw me out of their office. So we'll see what happens today. It'll be interesting to get your input. But what I want to do is set the foundation for what's happening with DDoS attacks today and what we're seeing in terms of the effects on IPv6 migration devices. This is kind of a new thing. If you keep up with Prolexic, Arbor, Radware, whatever your favorite publications are for what's going on with DDoS attacks, you'll find a new section around carrier-grade NAT and IPv6 migration. So these are becoming favored targets for the community out there that are attacking these infrastructures. So that's what I want to present to you today, and try to get your thoughts and feedback on that. So we'll just polarize the room right now. Who's using any kind of IPv6 migration strategy for either IPv4 preservation or seamless migration from IPv6 to IPv4? Anybody in the room today? Okay. All right, good. Ed, you're the guy. All right. All right, guys, so just a quick history lesson, staying away from marketing slides, but I don't want to assume everyone in the room is an IPv6 migration expert or DDoS expert. The bottom line is that these first attacks started showing up around 1989. They were very simple, single vector, ICMP flood-based type of attacks, and from that they grew around 95, 96 were the first high-profile DDoS attacks, I believe. And then those have continued to grow in both power and complexity. And, you know, I want to be clear, you guys may remember, a lot of us, unfortunately, are still playing video games. And if you were around the Sony PlayStation network around 2011, you might have gotten a lot of your subscriber information actually stolen. And there was a massive attack on Sony in 2011. And DDoS attacks are about rendering a service or a device unavailable. It is not about stealing any type of information, credit cards, that type of thing. Those are left in the purview of web application firewalls, cross-site scripting, SQL injection, those types of attacks. But DDoS attacks typically precede those types of attacks. And it's simply just it's a distraction technique. So if you can get your IT staff busy trying to figure out where is this huge volume of traffic coming from, you may be taking your eyes off some critical resources for a few minutes, and that's really all it takes. So it's typically why we see DDoS being very important, at least in the consideration of your security strategy as you move forward. So we've seen those attacks grow in complexity. So now we're seeing multi-vector attacks like we just talked about. So we'll see attacks coming from different angles, different sources into the infrastructure of a particular service provider, operator, mobility operator, or an enterprise. And simply, like I said, as a distraction technique. And finally, we're seeing that culminate into a 400 gig attack this year, which is absolutely amazing. So if you're not familiar with NTP amplification attacks, please figure out how that happens, why it happens, if you're vulnerable to that as well, because if you take an NTP amplification attack and you spoof on the addresses in your NAT pool, and 400 gigs starts coming into a resource on your IPv6 migration device, you got a big problem. And trying to solve that, I've seen customers, for instance, what you need to do is create a dynamic blacklist and surgically pull that IP address out of your pool. To do that, I've seen all types of gymnastics of creating multiple NAT pools, grouping them together, trying to isolate that CIDR block, and it's a real mess. So being able to identify when that attack is happening and have a proactive strategy for it is very important. That's what we're going to talk about today. All right, real quickly, like I said, I didn't want to assume everyone in the room has dealt with this before. So in most of the polls, hopefully you guys are represented there. We're seeing most of the concern in 2014, 2015 around actual infrastructure attacks. So there's different types of attacks on different levels aimed at different types of effects in your network. So the simplest ones are network volumetric attacks, network protocol attacks. These are very easy to conduct. You can do it at home. I like to have fun with the kids. Instead of grounding them, I'll just attack the home router so that their Xbox was working. And it's like, I don't know what happened. And of course, I get to fix it, so I'm the hero then. Anyway, these large-scale attacks, so they can take on, like an ICMP flood. Very simple thing to do. But what does ICMP typically require? It requires a response. Right? So there's a couple of things that happen with these types of attacks. Not only do they fill up the pipe themselves, they also force a particular device, depending on how it's architected, to go into a tailspin as well, trying to respond to all these ICMP requests that are coming in. This can render a box. Speed is very important. If you let this go on for long enough, a box can get to the point where you've got to manually intervene and actually go turn the thing off and back on. So speed is very, very important. And I think, there's some very good strategies. We're integrating with Defense for All. As complicated as using SDN, flow updates. There's a lot of things going on in the BGP world as well. And I don't have time to go into all that today. But it's critical that you're able to identify these attacks very, very quickly and mitigate them. And a lot of the architectures that are out there as far as using telemetry, SFlow, NetFlow, recognize this attack, go through the analytical process, compare it to your baseline, and then finally inject a BGP/32 to make this thing happen, it's too late. It's just too late. So you need some defense to react very, very quickly. And then, of course, that other piece is needed as well. Okay, so we'll talk about that a little more in a moment. TCP SIM floods, ping of death, LAN attacks, these types of things. These things are exposing issues, in the normal operations of IP, but they're, like with TCP SIM floods, right? So we're creating a situation where we are exhausting state within the box itself. Okay, so the firewalls, anything that keeps state, right? CGN devices, IPv6 migration, all these types of devices are highly susceptible to this as well. Those are the two main ones that we're going to be talking about today. Now, there are other types of attacks that are happening at the application layer, and I'll kind of leave that for your review if you haven't looked into it, but just basically targeting, inefficiencies or actually the proper operation of HTTP, but just causing, an overwhelming response of opening up multiple threads that basically never end. So there's a couple of ways to do this with HTTP GET, HTTP POST, and like I said, I'll leave that in the essence of time, let you guys take a look at that. But primarily, attack amplification is what is driving most of these large volumetric attacks now. So for NTP specifically, for you guys that manage networks, especially where you have an NTP server, typically these servers are very beefy. You've got a lot of guys connecting to them. You've got large drains coming into them as well. And, if you commit a monlist command, you could get back as many as 600 IP addresses, the last 600 IP addresses that connected to that actual server. So theoretically, you just from a single response, you could get a 200-to-1 amplification factor. So if you mix that with a reflection attacks, in other words, if I make a monlist request to several NTP servers and I spoof an address out of your NAT pool, then you're going to get back a 200-to-1. And sometimes I've actually seen, I haven't seen the math on it, but theoretically you could get up to like 517-to-1, depending on the number of NTP servers that are involved in these attacks, and completely overwhelm the data path in your CGN device. At the very least, you're going to have a customer SAT issue for a sector of your customer. Worst case, you're going to take the box down. Okay? Okay, just anecdotally, does anyone know why it's easy as 1, 2, 3 to attack with NTP? Yes. Yep. Exactly. And it's on port what? Do you know why? Do you know how it's as easy as 1, 2, 3 to attack with NTP? Yeah. And it's UDP port 1, 2, 3. Yeah, exactly. So send a monolith command over UDP 1, 2, 3, and you'll get back a 200 to 1 response. Okay. Just real quickly, guys. So the infrastructure attacks, like I said, I've already talked about this a little bit. The primary concern, and most of the operators I talked to out there are still around infrastructure attacks, right? It made up 80% of the attacks last year. And some of these are still very simple. The UDP floods, they're ICMP floods. And guys, you know, we live in a world where you can rent a botnet for $10 an hour to go out and attack anything you want. So you could have a disgruntled employee, you know, it really doesn't matter. So you've got to have some kind of strategy. And like I said, you've got to deal with this quickly. 4 to 5 minutes is not good enough when you're mitigating these types of attacks. So we need something on the perimeter. And a lot of the things that we're seeing around IPv6 migration is that box is becoming a favored target of attackers. There's a couple of reasons for it. It's very unique. And of course, I know I'm talking to a group that's like, okay, why are people using NAT 6.4? Well, NAT 6.4 is one of those things that actually is making IPv6 migration possible. I'm not saying CGN or NAT 4.4. I don't want you guys throwing things at me. But NAT 6.4 has the same problems. It's built around the same behavioral aspects of RFC, 6888, and all the behavioral drafts around TCP, UDP, ICMP. It just basically has an IPv6 client on the other side, right? So there are favorable targets. And in this particular poll, for the first time, I actually saw a breakout of those that have responded. This is either Arbor, I don't have my glasses on, this is Arbor as well, of those people that actually responded back and it actually admitted, hey, our CGN devices have been compromised. And, just I'll do the math real quick. About 50% of these had at least a moderate impact to a complete outage. Okay. So this is real, and it's going to continue to get worse because, like I said, these are favored targets. You can target these from a flooding aspect. I mean, at the end of the day, they're a router. So all the same things that a router has, all the issues around routing from exposure, denial of service attack is there. But at the same time, we can attack NAT pools. We've got connection setup issues as well. And volumetric attacks against NAT pool resources, again, these can cause a lot of problems. And if you're not familiar with endpoint independent mapping, endpoint independent filtering, hopefully you are. For the old guys in the room, we call this full cone NAT. But this is basically one of those things that makes IPv6 migration a reality for peer-to-peer networking. So Nutella, BitTorrent, Xbox, PlayStation, any peer-to-peer networking requires endpoint independent mapping and filtering to operate. Unfortunately, though, what it does, it's not like symmetrical NAT, right? If I have an external resource, and that external resource, regardless of its IP address and port, if it knows what the IP address is, and the port that's open on the session on the box, it can talk to that client. So it's basically like a wildcard. Symmetrical NAT actually tracks the destination address in the external network. Endpoint independent mapping and filtering makes that a wildcard. So now we're opening up the box to attack not only from the inside, but also from the outside. So an attacker can actually attack your IPv6 migration device. He can also attack through your IPv6 migration device directly to the client as well. This also indirectly affects your logging infrastructure, right? For law enforcement compliance, obviously we have to be logging these sessions. And if you've dimensioned your logging around a specific connection rate setup, which is really the metric that drives your logging infrastructure dimensioning, you could be affecting your logging as well, indirectly. So I kind of broke this down into 5 sections. This is I hear about other features as well. These are kind of the 5 cornerstones that are consistent with the customers I'm dealing with today from an IPv6 migration standpoint. First is packet anomaly check. Packet anomalies it's very easy to turn these on. Most of your routers support this today, depending on how much they support it and depend upon other DDoS measures or mitigation measures. That's going to vary from vendor to vendor. The bottom line is, though, it's very easy to turn these on. And they're an easy They're an easy technique for your frontline defense in your individual infrastructure. This might be new to you. Dynamic blacklisting of NAT pool resources. So for the IPv6 migration device to actually detect that it's being attacked, that there's a IP resource in the pool that's coming under attack, and then actually blacklist that. And we can also mix this, if you guys, something we call auto black holing, but basically this is just automatic remote triggering of a black hole route. So you can actually get around cleaning, you can get around using a DDoS scrubbing to clean the pipe by simply, once you realize you're under attack, actually automatically sending a remote black hole trigger to your upstream provider or to your upstream routers to begin to black hole that as well. We'll talk a little bit more about that in a moment. External interactions. So this is mainly from the mobile operators, but interacting with things like PCRF, radius servers, diameter servers, and what have you, right? So if attack has happened and we're on the front line, and for some reason we did not mitigate that particular attack, we need policy awareness with what's going on in the network with the upper layers. So this is both for your DDoS defense methodologies, so for actually detecting the attack and also for reporting that attack as well. Session setup rate, traffic rate control, so the ability to identify each individual source IP address, regardless if it's on the outside of the network or the inside of the network, and properly keep that within some policy for rate limiting. It's also very important. This also comes back to telemetry. We have to understand our network. We need what is normal, what is the baseline, and identify anomalies within that and then be able to take action. And then session setup rate. So again, when you're dimensioning your IPv6 migration infrastructure, a couple of things come to mind. The number of concurrent sessions that I have or that I can support, the actual connection setup rate, because that's also a finite resource within the device. Okay. So for instance, if you can only support 500,000 connections per second, I can amass a botnet behind your IPv6 migration device if you've not properly set up your port limits for UDP TCP and you're letting it basically run wild or run to some artificially large number, then I can actually cause that box to go down by exceeding the connection per second rate, depending upon the architecture of the device. Okay. So let's look at the simple ones first. I want to kind of reverse these. ICMP rate limiting. Doesn't sound very sexy, but at the end of the day, this is something that almost every device supports, even in hardware. Turn it on. Right now, as we move from IPv4 to IPv6, obviously ICMP is very important in the operation of the IPv4 network. It's even more important in the IPv6 world as well. So we have to do this very intelligently. The bottom line is that 10% of the infrastructure attacks occurred with ICMP last year. And those particular attacks, like I said, are particularly crippling because they can fill up the drain to your upstream ISP. They also have the effect of causing the box to begin to reply to those responses, either port unreachable, destination unreachable, or maybe it's just simply just an echo request, echo reply. But it causes the box, and depending on how it's architected, this could cause some issues in the box as well. So it has to be done intelligently. I've seen different types of mitigation strategies around this, but having a low-level watermark and a high-level watermark, and in between that having almost like a random early discard type of infrastructure where you're beginning to knock these things down indiscriminately, but also randomly. So we need ICMP to work, obviously. We don't want to just shut it down. There's a point where you're going to have to lock it up, though. So that would be the high water mark. So be able to have just a lockup rate for 5 seconds, 10 seconds to try to desynchronize the storm itself. Now, this also will help with like UDP flooding and other attacks that are going to elicit an ICMP response. So if you get a UDP flood, your box is going to send an ICMP port unreachable, obviously. So this will also help with those types of indirect ICMP attacks as well. So IP anomaly filters, we talked about this. These are based upon signatures, and I believe there was some discussion around signatures today as well. But basically, we're not looking bit by bit. We're looking for a particular signature, like a land attack. We've got an identical source address, destination address. Okay, it's pretty easy to apply a filter and find that. So basically, we're looking for basically a sanity check of the IP TCP protocols, UDP protocols, and at the same time, are we adhering to the standards in concordance with the state machine? So why am I seeing a TCP reset for a session that I don't even have? those types of attacks, where the control flags are being manipulated, et cetera. So specifically, those are going to come in basically three different types of batches. One that are some of the deficiencies in IP itself, right? Land attack, where the duplicate, you could have duplicate addressing in the source and destination fields. Others where I have valid IP packets, but I'm getting unexpected type of values. For instance, none of the flags in the TCP header are set. So that's like a null attack, if you will, right? Other like ICMP ping of death is very good, where I'm sending just an exorbitant MTU size for ICMP. Those types of attacks can be handled as well, simply by turning on anomaly filtering. And then finally is just the operation of the protocol itself. This is where TCP send attacks, where we're not completing the three-way handshake, and we have so-called half-open connections. Fragmentation attacks, where we have overlapping fragments, missing fragments, duplicate fragments. Those types of things fall into that. So IP anomaly in itself will provide a nice security gate for you. But taking that forward, let's look more at the connections themselves. So I walk into so many customers, and one of the things that you have to determine when you deploy your IPv6 migration strategy is how many TCP UDP ports am I going to give that subscriber on the IPv6 side of the network? Do I give them 1,000 ports? Do I give them 2,000? Do I give them 500? What do I do? Unfortunately, what I typically see is a simple mathematical exercise. I got X number of IPv4 addresses, I got X number of IPv6 clients, do the math, and that's the number of ports I use. Usually that comes out to be a very large number. I'm not going to name them. There are several very large Tier 1 providers that are our customer that, I'll see 8,000, 10,000, 12,000 ports per customer, up to an 8-to-1 oversubscription rate, around 8 to 12,000 ports again. You're setting yourself up for an attack when you do that, because what's going to happen is that is the absolute total number of ports that I can give any individual subscriber. And in itself, that's not a problem. The problem happens is when I amass a botnet on the inside of your network, and I've got 100, 200 subscribers, and I have them start blowing these things out, with spiffed addresses. And I can blow that CPS number out very, very quickly. Depending upon the vendor, some of those vendors are going to recover quickly. Some of them will not recover at all. Okay. So understand how your box, during your POC, if you're using these types of devices, make that part of your strategy, this negative testing, to determine exactly what the characteristic or the behavior of that box is going to be if that happens. Now, this also is very applicable to endpoint independent filtered sessions. So these are those sessions coming from the outside to that client. Okay, so just real quickly, go through this again. Peer-to-peer networking. I have a rendezvous server thing. Everybody uses BitTorrent, or everybody in here probably has used BitTorrent. BitTorrent's got a tracker. That individual tracker is going to build a swarm, and he's going to give your endpoint IP address and source port to those individual devices. They don't know you're behind a NAT device. So literally what they did is they handed off your NAT pool assignment. And they're going to come in there and try to talk. In a symmetrical environment, that breaks. An endpoint independent mapping and filter, that's allowed. So basically what that means is an attacker that can guess in a specific time, sorry guys, what your IPv4 resource CIDR block is for your NAT pool and the port that you're running. They can attack your device. They can either attack your device or they can actually attack the client behind it. So the source rate limiting is also very important from a connection standpoint, coming from the outside to the inside as well. So this is probably the most important feature, the ability to blacklist a particular NAT pool resource after it's come under attack. So the way this basically works is you define a filter. Again, telemetry is very important. You need to, in deep packet inspection, you need to understand what this number should be. Is it 10,000 packets per second? Is it 30,000 packets per second? But actually, once that threshold is reached, you create a tuplet in hardware, if you will. And that hardware is checked every time a packet comes in. And when that packet comes in, it will be dropped immediately. Until such time that it comes under a specific baseline within policy. for that particular device. So what this does, there's a couple of things that happens. You can attack your NAT pool from the inside or from the outside. Most people don't think about that, but you could actually create a botnet that could attack, because it's like a loopback address. On almost, I haven't seen any device that doesn't work this way, actually. But that NAT pool address sometimes is even pingable, and we'll talk about that in a moment. But they can reach that NAT pool address from the inside. They can actually attack it from the inside. If they do that, or they're actually going to affect the box and everything in the data path as well. So if you think about, let's think about a fictitious L4, L7, router based upon x86 architecture using, CPU, a symmetrical multiprocessing environment. Typically, what happens is you'll hash those sessions to a particular CPU. So when that NAT pool address comes under attack, that CPU creates a hotspot and it goes to 100%. So not only is everyone affected that is mapped to that individual IP resource, IPv4 resource, everyone that is using that CPU is also affected as well. Okay. If the botnet, if you reverse the attack from the inside, and that NAT pool address is being used, for not so noble causes, what's your upstream ISP going to do? They're going to blacklist that IP address. Now you've got a real problem. Now you've got a surgical /32 out of your IPv4 resource pool that's not available. And you have to go, like I talked about, into all this process of trying to solve that problem and get that mitigated. So bottom line, the way this works is either from the inside or outside, if the packet's going into that specific address or compromised and they exceed the watermark, you create a dynamic blacklist for that IP address immediately. You drop all traffic to it. The next step that I would recommend as well is when that happens, this triggers a compromised route map, and that compromised route map actually is a remote trigger for a black hole above that. So one of two things has got to happen. Once this happens, if the attack is large enough, your pipe is full. So regardless if you mitigate the attack or not, that drain is full, and that in itself can be crippling. So you can either take care of that through the typical manner of using a cloud-based DDoS infrastructure solution. That's going to take a while. It'll take 2 to 3. A lot of times it's a manual process. It's not even an automated process. Or you can use remote trigger black holing. And if you're not using this feature or familiar with it, I would ask you to take a look at that. It's pretty simple. But basically, you create a compromised route map, and for most manufacturers, it's a manual process of where I'm going to notify upstream routers. I might own them. They may be in another AS. To basically send all traffic that's coming to this specific next hop, send that to the null interface. So this is another way to clear out that pipe as well. In this specific, the way that we've actually implemented this is once a tuplet is written into the hardware table, we immediately will send a remote trigger black hole for that. Of course, it's configurable, the timing, and how elastic you make this process, but we can actually automate that process as well. So let's talk about telemetry as well. So if we're on the edge, if we're on the perimeter of the network, and we're actually mitigating, these DDoS attacks, then we've got to be giving you the correct visibility as well. Several ways to do that. IPv6, S-Flow is becoming more and more popular since with the advent of S-Flow real-time. S-Flow RT can give you a very, very fast response to an attack that's coming into your network as well. Supporting common event format logging. You're going to have a lot of boxes in your network that support S-Flow or they support NetFlow. Different types of devices and going to different destinations, different formatting. So using CEF logging format is very important as well. But we need the telemetry first off to baseline the network, right? We also need the telemetry to also flag any DDoS infrastructure that you're using for detection, that we have an anomalous event happening as well. So this is just time series data. There are millions of these control blocks now. It's amazing how much information that you can get from your network. In this case, we're sending this directly from the CGN device itself, or the IPv6 migration device. So just real quick, guys, I want to throw together just a quick best practices guide for you, some things that we see and we recommend to each one of our customers. This one's simple enough. a lot of time, I don't know why. I don't see a judicious use of access control lists in the network. This is very simple to do. Use ACLs, right? Just you guys know how to use them and where you should use them and why. But we don't really see OANM access lockdown, internal threats, that type of thing. The other thing is that if you're in a one-armed environment or if you're in an inline environment, typically, depending upon your vendor, you're going to use either an access control list or you're going to use a class list or whatever your manufacturer calls it, but basically it's a classification to determine which IP address is coming from the inside that we're actually going to process as IPv6 migration clients. A lot of times I see that simply as, send me everything. This is bad because this allows a botnet to actually spoof addresses behind your network. You don't want to allow that to happen. So explicitly configure, 100.64/10, 192, whatever it is that you're using, explicitly configure that in your class list. And on top of that, if you have the capability, set basically, add that for anything else, we want to override and drop that traffic. So just basically have an implied denial at the end of that as well. The other thing we haven't really talked about is disabling inbound refresh. So there are basically the sessions are going to be refreshed by seeing traffic from both the client and externally. So this can lead to issues as well where the client basically is always under attack, policy within the network, somewhere outside of the IPv6 migration network, shut down that connection. If it's a mobile operator, he shut down the bearer, tunnels are down, what have you. But the bottom line is that the external resource is still sending the flood. So what's going to happen? I'm going to send UDP port unreachable. I'm not listening on that port anymore. So this kind of exacerbates the problem. So there's a feature that most of the vendors support now called inbound refresh. So basically, if we don't see the packet coming from the client, we are not going to refresh that session. Now, TCP state rules, TCP reset, FIN-FINAC, these sessions should be taking care of themselves unless they have been compromised. UDP is really the problem, and different types of tunneling as well that depend upon UDP. Also, understand your box's TCP send defense method. They all have one. Some IPv6 migration devices are basically a TCP proxy. So they're terminating the TCP session. If that's so, implement some kind of authentication that could be TCP send cookie, whatever it is, but turn that on if your box can deal with that at the either at wire rate or at the rate that your customers are sending the traffic. Others just simply monitor the three-way handshake. They're not a proxy. They're transparent. And it'll be based upon a timer. Okay, if the TCP three-way handshake doesn't occur within 3 seconds, then shut down the session. So understand how your particular box is dealing with this, and then implement accordingly any measures that you need to take to protect it. Again, optimize subscriber port allocations, right? We call this user port at 810, but these are your port limitations. You don't want to give the customer 8,000 ports, 12,000 ports, unless they're a heavy BitTorrent user. If they're a heavy BitTorrent user, they're not a candidate for IPv6 migration in the first place. Just give them a direct conduit through your network and run them through your firewall. Disable ICMP ping response. Now, this may be considered a bug. I know early on a lot of manufacturers would allow you, and this was by default, to ping anything that's within the ICMP or within the NAT pool, excuse me. So make sure you disable that as well. The other thing we haven't talked about ALGs, so application level gateways, right? Application layer gateways, so SIP, TFTP, and what have you. If you have done the proper things to control your endpoint independent mapping, endpoint independent filtering, targeted vectors into your box, make sure you understand how your ALGs work. For some vendors, let's take TFTP, right? TFTP, you're going to set up a session from the client. Whatever it is you're talking to on the outside is going to randomize the source port and send it back. Well, I just basically described the full cone NAT session. So a lot of these TFTP, especially TFTP SIP, is the same way. We'll turn on endpoint independent mapping and filtering for that session regardless of what your global settings are. So that's going to open up a pinhole, if you will, in your network for a short amount of time that an attacker could use. Again, limit the endpoint independent mapping, endpoint independent filtering capabilities. Typically, you have the ability to control this right down to a port level, a lot of times I just see it turned on. And it does need to be turned on because you've got the Xbox networks, you've got PlayStation networks, anything that's peer-to-peer is going to be dependent upon endpoint independent mapping and filtering. Also understand your stun timers, all right? So this is a specific timer that will shut down your endpoint independent mapping and filtering sessions. A lot of times it'll default to, I think the default actually in the standard is 2 minutes. Typically you need 4 minutes for Xbox to work correctly. A lot of times those sessions will go silent for 4 minutes. If you shut them down and that client tries to come back in, well, you just broke Xbox, okay? So control those timers as well and know that they're there. The other thing to do for law enforcement compliance, if you have the capability, correlate the logging directly in the IPv6 migration device itself. So most of the logging implementations are quite feature-rich now. So we have the ability to, for our mobile operators, we embed MSI-SDN and IMEI information directly in the log file so that when they're looking at a private IP address, which really means nothing to them, they have the subscriber information that they need to very quickly correlate and go out and provide arbitration for the law enforcement. This can be done for our wireline provider as well, using different radius attributes, right, for that particular user. The other thing to understand is that I talked about kind of a layered approach, right? I've got ICMP rate limiting, I've got other rate limiting on connections themselves. I've got what we call selective filtering, which is protecting the NAT pool itself. And then we got IP anomaly filtering. A single attack can match a signature for all 4 of these, so which one takes precedence? It's important to understand which one will. For instance, an ICMP attack could match. This could be a ping of death attack. It could match or override the connection rate limit. It could override the connection limit that we set in selective filtering. So which one of these is actually going to mitigate the attack? This is a very important point. And the reason I bring it up is that some of these are going to be implemented in software on your box. Some of them are going to be implemented in hardware. And we don't really want software processes dealing with DDoS threats. Okay. And with that, I'm going to close and open it up for questions. Yes, John. If you ask me a question, I've got one for you later too.
See if it's on. There we go. Specifically on IPv6 and DDoS mitigation, you mentioned one of your slides about blacklisting. I've seen a lot of people very concerned that there's no way you can enumerate all the V6 addresses you might want to block, right? One subnet is 18 quintillion addresses, and we're seeing some of the DDoS mitigators we work with say, you need to put all your addresses in like a /120 range, so that if I have to do an ACL, it's not going to be too big. What is your advice on blacklisting in an age of ubiquitous addresses?
So I'm going to answer that from an A10 network's perspective. Okay, so exactly what you said was the only technique that you had. In the latest release, we just released the ability to surgically remove an IP address from the actual NAT pool. So now you don't have to go through either what you said, dividing up the NAT pool and creating a NAT pool group to minimize the CIDR block that you'd have to take out during an attack. But also, if I can mitigate that in real time, I've kind of solved the problem as well, because now that's a dynamic process where I can actually identify, okay, I've got an attack on this particular resource. Now, I may be affecting 1,000 users behind the device. I don't know how many are actually mapping into that particular IP address, but at the same time, that's a much easier pill to swallow than the actual attack mitigation is going to or the attack propagation is going to happen through the network. So that's a very valid technique, but if you do have a manufacturer that can surgically remove that IP address from the pool before it's, or if it went so far now that's blacklisted deeper into the internet with other service providers as well, or provide this technique, it will solve that issue, John. Yeah.
Hi, I'm Cole Jepkis. I'm an engineer with A10. I just wanted to take a quick moment, if you don't mind, Glenn.
No.
We had a drawing for people who dropped their business card in our hole there at their desk. So we're giving away a free backpack. I just wanted to check. You don't have to be present to win, but is Scotty Dawson with CSU here? Scotty Dawson? Come on up. Yay! There you go. You bet. Thanks for giving me the time.
Anything else, guys? Thanks, everyone. Have a good day.
All right. Thank you very much.